Welcome to this explainer. Today, we're diving into something that is literally one of the highest stakes topics in our modern world. I want you to just kind of slow down for a second and really think about this. A single line of code, written on a random Tuesday, has the power to completely alter a person's life. We tend to think of algorithms as these flawless, perfectly objective tools. But the truth? It's way more complicated, and honestly, far more fascinating. Today, we're going to learn step by step exactly how to build responsible machine learning systems. Okay, consider this quote. Machine learning is powerful, but it is not neutral. We really need to shatter this common illusion of objective AI right out of the gate. A machine learning model doesn't understand the world the way you and I do. It's not a person. It simply learns patterns from data. And since that data comes from the messy real world, those numbers actually just reflect human flaws, human history, and, yes, human inequalities. So here's our roadmap for today. We're going to cover the myth of neutral AI, what to do before you even start building, handling data and labels, training your model, real-world deployment, and finally, human accountability. All right, let's jump straight into section 1, the myth of neutral AI. You see, models are essentially just highly efficient pattern-matching machines. And because they apply the exact same decision process millions of times in a fraction of a second, they can amplify historical imbalances on a massive scale. To prevent these automated disasters, we have to look at the entire machine learning lifecycle. Notice how model training is actually step 3 here? That's right. Ethical issues can totally infect a system long before a model is even trained. By the time you actually sit down to write some code, your whole project might already be compromised.
Which brings us to section 2, step 1, before you build. I really want you to ask yourself the very first and honestly, arguably, the most absolutely crucial question of responsible AI. Should machine learning be used for this problem at all? Just because we can predict something definitely doesn't mean we should. Imagine a college uses an algorithm to predict which students are likely to drop out. Now, the math behind the model is exactly the same in two very different scenarios. In the first scenario, if the college uses that prediction to offer extra tutoring or maybe financial support, well, it's a wildly helpful tool. It's saving academic careers. But in the second scenario, if they use that exact same prediction to deny admission or label a kid as a lost cause, it actively destroys opportunities. The algorithm didn't change at all. The human application did.
Okay, moving on to section 3. Step 2, data and bias. So once you've decided a problem is actually worth solving, you need data. But the reality is, data is never perfectly objective. Why? Because it's collected by flawed human institutions. Let me walk you step by step through a real-world example that's kind of terrifying. The feedback loop in predictive policing. Systems often use historical arrest data to predict future crime. But here's the catch. Arrest data doesn't necessarily represent all crime. It represents where police have historically patrolled. So step 1, you have more police presence in a specific area. That leads directly to step 2, more recorded incidents. Then, step 3, the model sees those incidents and predicts more crime there, which naturally leads to step 4, recommending even more police to that exact same neighborhood. The model is technically working perfectly, but it's just feeding on a vicious automated cycle of historical data. Now, there's a really common trap that developers fall into here. They think, oh, I'll just delete the columns for race and gender, and boom, my hiring algorithm will be totally fair. But look closely at hidden proxies. If you leave in zip codes, specific extracurricular activities, or career gaps, the algorithm will ruthlessly find mathematical patterns linking those things directly back to race or gender. Deleting sensitive columns doesn't fix bias, not at all. It just hides it, which allows the machine to recreate historical hiring preferences in complete secret. Let's dive into section 4. Step 3, training the model. All right, so you have your data, you're writing your code, and you are naturally trying to make the model as highly accurate as possible. But here's the thing, optimizing solely for accuracy completely ignores some severe real-world risks. To understand why, we really have to look at the kinds of errors a model makes. A false positive is when the model predicts something is true, but it's actually false. A false negative is when it predicts something is false, but it's actually true. I want you to just pause for a second and really digest the difference between these two. Because in a lab, they're just statistics, but out in the real world, they can literally be life-altering. Look at how context changes absolutely everything. In spam detection, a false positive just means a harmless email ends up in your junk folder. It's annoying, sure, but in healthcare, a false negative means missing a serious disease in a patient who desperately needed treatment. No way around it, that's catastrophic. In criminal justice, a false positive means assigning a high-risk score to a low-risk person, which can lead to an unjustly harsh prison sentence. So you can't just ask, hey, how accurate is the model? You absolutely must ask, who is actually affected by these errors? This builds directly into another really vital real-world case study. Imagine a healthcare system wants to predict which patients are at high risk and need extra care. Sounds great, right? But the label they used to train their model was past healthcare spending. They basically assumed that people who spent a lot of money on healthcare in the past must be the sickest, but they completely missed the patients who simply couldn't afford care, lacked insurance, or faced other structural barriers. By using financial spending as a proxy for physical illness, the model dangerously underestimated the medical needs of incredibly vulnerable people. As we train these massive models, we constantly run into complex issues of fairness and transparency. First off, fairness is incredibly hard to define mathematically. Equal opportunity very often conflicts with equal outcomes. But more importantly, transparency isn't just some technical issue. It's really a human right. If a person is denied a loan or a job or flagged as a security risk by some black box neural network, having a data scientist just point at feature importance scores is simply not enough. People absolutely deserve a plain language explanation of why a machine just altered the course of their life. Moving right along to Section 5. Step 4. Real-world deployment. Okay, so you've built the model. It works perfectly in the lab, but here's the wild part. A project can run beautifully in your notebook without a single technical error, while still containing severe ethical poison once it hits the real world. The absolute biggest danger at this stage is automation bias. We humans have this dangerous tendency to trust computer-generated outputs way too much, simply because numbers look scientific and objective. If a model spits out a risk score of 87%, a human operator is highly likely to just blindly follow it. We cannot encourage users to do this. A responsible system must force humans to understand the model's uncertainty and its limitations. Furthermore, ethical machine learning definitely does not end on launch day. Have you ever heard of model drift? It's basically when a model slowly fails because the world around it changes. Economic patterns shift, medical practices evolve, and social conditions adapt. A model that was perfectly fair and highly accurate on day 1 might completely degrade and become heavily biased by day 300. If models aren't constantly monitored, they will just rot. It's that simple. Post-deployment, we also face some pretty intense ongoing real-world threats. First, we see facial recognition systems suffering from much higher error rates across different demographics, which can lead to false arrests. Second, we see bad actors intentionally poisoning training data to manipulate AI outcomes. And third, we really can't ignore the massive environmental impact and energy usage of running these giant models. Sometimes a simpler, cheaper, and more transparent model isn't just ethically superior, it's environmentally necessary. And that brings us to our final section, Section 6, Human Responsibility and Accountability. It is officially time to shift our focus away from the code, away from the data, and directly onto the humans who write it, deploy it, and trust it. You need clear, actionable instructions to prevent your systems from doing harm. So, here is your definitive responsible ML checklist. Before building, is machine learning actually necessary? During data collection, are the labels reliable or are they just historical proxies? During training, does the model's performance drastically differ across different demographic groups? And finally, at deployment, can affected people appeal the machine's decision to a real human being? Let me be clear, if you cannot answer these questions, you are simply not ready to launch. I want to leave you with this final provocative thought. If an AI system causes actual harm out in the world, who really takes the fall? Is it the developer who wrote the code, the manager who approved it, or the end user who just blindly trusted it? AI systems have this way of making responsibility feel incredibly murky. We love to say, well, the model made the decision, but models do not carry responsibility. They are just math. Only we can carry responsibility. Thank you so much for joining me on this explainer. Until next time, stay curious and build responsibly.